All right, hello everyone. Welcome to our talk under the sediments V2. I'm Brock and I'm here with Denny. I'm a software engineer at Databricks, and that's basically it. I'm gonna go and grow a beard and change real quick, and Denny can introduce himself.
Thanks very much, Barack. My name is Denny Lee. I'm a dev advocate, and now I'm going to have to change my shirt as well.
All right, let's get started. So today we're going to look underneath the sediments of a Delta Lake table. To do that, we're first going to analyze our Delta log, which is the transaction log, and it's the key component to Delta's ACID capabilities. Then we're going to look at time travel, how Delta's transaction log provides time travel capabilities, and then also look at how Delta plans and executes batch and streaming queries. And then we're going to see it all in action by a demo from Denny. So first of all, let's start with the transaction log. Let's see what's going on, how Delta looks, actually, a Delta table looks on disk. So you have your directory of your table. Under this directory, you'll find your transaction log in this _ Delta log directory. Within this directory, you're going to find table versions. So small JSON files that actually contain the changes that are being made to your Delta table. And these are actually called Delta files. You can optionally find partition directories of how your data is stored. Delta doesn't actually need to store data inside partition directories. It's just a cosmetic, feature for Hive tables. And then we also have our data files stored alongside them as well. So if you were to open up a JSON file, what would you find inside? Inside, you'll find a set of actions. And what these actions represent are changes that are being made to your table. So the first critical one is essentially the metadata, updating the metadata of your table. Within your metadata, you contain information such as the name of the table, the schema, the partitioning that you're using, and a lot more, like the table properties and such. If you were to change the schema of your table, you'll see an action of update metadata being committed to your table as well. Then you have your add file actions. Add file actions basically say, hey, I've written this file, committed to your log so that the next time a query comes, I actually read the information from this file. We put in the information such as the path of the file, the partition values that it's stored for, and as well as, optionally, we have statistics per columns, and you'll see all of that from Denny's presentation, Denny's demo. We can have remove file actions. These essentially say, hey, remove this file. This can be due to like a compaction operation where you're compacting files into one, or these could be due to like delete operations that you perform on a Delta table. We have our set transaction action. These set transactions record an idempotent transaction ID. So this is used mainly by structured streaming. And essentially, it's every stream keeps track of how many batches it has already committed to your Delta table. And this way, it becomes a very cheap operation to actually see if your stream restarts, whether data needs to be reprocessed again or recommitted to your Delta table. Then we also have our protocol action. And what this provides is essentially, the cool thing about Delta is that it's just a transaction log on top of a object store. So, and you're using kind of like a library to read the transaction log and reason about what data that, should be queried and such. So the protocol information tells you whether, your current library, whether it's your latest Databricks cluster or, your Delta Lake jar that you download from Maven can actually read the transaction log correctly. And in the end, you get a result of, what's the current metadata of my table? What are the list of files that I need to query? What's the version, so on and so forth. So one of the cool things about Delta is its ACID transactions. And so how does Delta provide atomicity, the first letter in ACID transactions? So the changes to your table are stored as ordered atomic units called commits. And as we mentioned, these are your Delta files that are being committed to your table. What happens is you first write out all your data files, and then you commit it to the transaction log. So for example, here we're committing the addition of files 1 and 2. And in that case, once we can find this version in the transaction log, we'll know that we can read files 1 and 2. For example, we can commit version 1 on top of that. And here we're saying, oh, I'm removing files 1 and 2, just read version 3, file 3. And this way, if you were to query a Delta table at version 1, you would just read the file 3. And then if that's atomicity, let's talk about concurrency and serializability. So we need to agree on the order of changes that are being made to your Delta table, even when there are multiple writers. So how does that work? For example, user 1 could be reading, for example, it's going to mutate your Delta table. It might be running a merge operation, for example. It will start from reading from version 0. At that time, user 2 actually starts. Someone else has written version 1. User 2 reads the version at version 1. And it tries to commit version 2, but what user 1 doesn't know is that version 1 and 2 already happened, so user 1 will have to reason about conflicts within these two commits. So how do we reason about these conflicts? Well, with Delta, we solve conflicts optimistically. This was a pretty important design choice where we discussed that, analytical operations will typically be non-conflicting, meaning that we're generally going to be appending new data to our table rather than continuously updating, certain rows over and over again. So what happens is when two writers are trying to write to the Delta table, first they'll record their start versions, which version was the table at before, a transaction starts. It'll record all the reads and writes it performs during that transaction. It'll attempt to commit. If some other writer wins, it'll have to check if anything you read has changed, and then it'll try again. So for example, user 1 and user 2 could start at version 0. They'll read both the schema at version 0. And what they're doing is they're just blindly appending data to your table. For example, two streaming jobs, appending data to the same table. User 1 will win, commit version 1. And then in that case, user 2, what it'll have to do is see what changes have been made in this version 1. Since it was a blind append, user 2 is going to say, hey, I'm also a blind append. I don't need to worry about it. So what it'll do is it'll immediately commit version 2. It doesn't have to rewrite all the data files again, since there was no, logical conflict of what these two users were doing. On the other hand, if there were, logical conflicts, if user 1 had deleted a file which user 2 is also deleting or has to read, then user 2 will throw an exception saying, hey, there's been a concurrent modification. Then you might say, well, okay, so Delta is great, it provides ACID, but how do you handle your metadata? One of the key pieces of Delta is that it handles its metadata internally. It doesn't depend on the Hive metastore. The problem there is, the problem with the Hive metastore is you have all the information for all your tables stored in one database being accessed by many, many clusters and many different execution engines at a given time. So this one database can easily turn out to be the bottleneck in your operations. So what we do instead is Delta handles the metadata itself. How does it do it? Well, it uses, for example, Spark to actually compute its metadata. And this is beautiful because each cluster then becomes, a stateless replica of your Delta table. Therefore, you don't have this many concurrency issues. You don't have this single point of failure and such. Then you might say, well, okay, you might be reading and using Spark to read all these JSON files, but won't you have a problem of too many small files? Well, then you're right. And for that reason, what Delta also uses is a technique called checkpointing. And what we do is, given every 10 commits right now, for example, we would replay all the actions, see what the latest state of the table is, and dump it to, a collection of Parquet files. And then Spark can actually query this checkpoint directly, and, it doesn't have to read all the preceding JSON files to compute the state at a given version. So More about these checkpoints, well, they contain the latest state of all actions at a given version, and they obfuscate the need to read all these small JSON files. Why do we choose Parquet for the checkpoints? First of all, there's no parsing overhead with Parquet, similar to JSON. So if you have like a huge table, instead of having like a gigabyte sized JSON file, you'll have like a small megabyte sized Parquet file. And also you get column pruning capabilities. You don't need to parse the JSON, as well as you can also read certain columns directly from the Parquet file, which can speed up many metadata operations. So how does Delta compute its state? So what we'll have to do is we'll have to list the transaction log directory. We'll find the JSON files that we see, and then we will use Spark to play those actions in order to compute the latest state. Once we compute the latest state, we'll cache that version in memory so that any operations on your Delta table after that can reuse this cached version and not have to do this state computation again. If we were to update Delta state, what we'll do is we'll list from, first of all, if we're at, version 0, or we're just, a new cluster, we'll list from version 0. We'll get our list of files. So here we've gotten 7, changes to our Delta log. We'll use Spark to compute the state. We'll cache version 7. The next time, we'll again list from version 0. We have our cached version 7 in memory. But here we see, like a checkpoint file appear, and then additional JSON commits have been made. So once we see a checkpoint file, we'll actually use that checkpoint file and play the JSON files after that for our log replay, and we'll cache the version 12 there. And the next time, we'll use our latest available checkpoint version. So we're using version 10 to perform our list, and then we'll see that, okay, we're at version 14. We can compute the version 14 and cache it and use that. So that's how essentially the transaction log works. Let's see how time travel works and kind of its limitations. So since we have our order transaction log, we can actually go back in time and replay to any given point of the transaction log in time. So with Delta, you can time travel by version and timestamps. To time travel by version, you can specify the version as part of a version as of syntax, an at syntax after your table identifier, or within Scala or Python, you can provide the version as of table options and provide which version you're reading, as well as just provide the version that you want to read appended to the end of your directory. And Delta will figure out, okay, you want to read version 1071. I'll just compute the snapshot at 1071 and give you the answer. If you want to time travel by timestamp, the access is very similar. You can use timestamp as of and provide, a date column or a date expression. And if you want to use the at syntax, you need to provide your timestamp in this year, month, day, hour, minute, second, milliseconds format. And you can also, again, provide a timestamp as of option for your Python or Scala readers, or you can also append it to the end of your path. But what happens with timestamps is that we don't know specifically which version that timestamp corresponds to. So we can't just delta log get snapshot at. So what do we have to do then? We need to figure out which version that timestamp corresponds to. So the commit timestamps come from the storage system modification timestamps. The storage system could be HDFS, it could be S3, it could be ADLS Gen 2 on Azure. What these systems provide, they unfortunately do not provide or guarantee monotonically increasing timestamps with our versions. These are distributed systems. There could be clock skew. Therefore, what Delta has to do first is to put these timestamps in order. So we have some timestamps from important moments in Turkish history here. And you can see that the last version is, the timestamp of the last version is before the timestamp of the previous version. So what we have to do there is, if timestamps are out of order, we'll just add 1 millisecond to the next version's timestamp to put them in basically temporal order. And when you want to actually query your data, given your timestamp, what we do is we play Price is Right rules. So we pick the closest commit with the timestamp that doesn't exceed the user's timestamp. So here, given 1492, we can select version 1071 because it was at 1453, and that's the latest version that's before the user provided timestamp. And then we can just compute our snapshot at 1071 accordingly. If you want to learn more about time travel, we have our time travel deep dive session tomorrow at the exact same time. So check that out. So some of the limitations, first of all, we require the transaction log files to exist. Delta performs log cleanup by itself automatically, and it performs this log cleanup according to this log retention duration setting. Therefore, you can time travel at most as back to this date. So if you want to time travel more than 30 days, which is the default, you would need to set this setting. We also require the data files to exist. Therefore, we have a different setting for this called the deleted file retention duration. And you might want to set these two to the same value of how much you want to time travel back. The limitation here is if you vacuum, you lose data. And that's why we have this deleted file retention duration, which prevents files that have been removed from Delta state to be actually deleted. They're kept around as tombstones. So given these two requirements, you can assume that time traveling in the order of months and years may be infeasible. The reason for this is that if you actually have a stream appending to your table, changing data every minute, you're going to have commits happening every minute. This could cause like your storage costs to increase, as well as computing Delta state won't scale when you have like millions of JSON files that you have to read at a given time. But what you can do to work around that is to use, for example, an operation like clone to archive your data once a day to some archive location, and that can actually provide, one change per day is not that bad to time travel back 10 years. But one change every minute will be pretty infeasible if you want to time travel back like even a month. So how do batch and streaming queries work on Delta tables? Well, batch queries are easy. First of all, we update the state of your table, showing, like how we shown before. We perform the data skipping, given your filters. And we filter the add file events in our transaction log according to the metadata. For example, the partitions and stats. And then given our reduced set of, we call it the read set, you can execute your query based on those files. How do streaming queries work? Again, we update the state of the table. And then if you've provided partition filters, for example, process all data since the last month, we can perform our partition filter, and then we'll cache the snapshot. The snapshot will start processing files in it, 1,000 files at a time by default. This is to prevent a batch being spawned for like 10 million files, which will your driver. And within this first set of files, there is no guaranteed order while we're processing the files in our snapshot. Instead of max files per offset, you can specify max bytes per trigger, for example, as an option to better set how much each batch of your stream should process from your Delta table. For example, you might want to process 100 gigabytes every single micro batch. Once your snapshot is over, then we'll start tailing the JSON files, the Delta files within your transaction log, and this will become very cheap. All we have to do is see what files have appeared within your Delta files. Well, you might say, I do compactions. I rewrite my files all the time. How does my stream interact with it? Well, if you have compactions, for example, if you run Optimize within Databricks, compactions are committed with a flag called data change equals false. And the streaming source is smart enough to skip over any file that has this data change equals false setting. So if you compact your data, you won't actually reprocess, duplicate records. if you actually delete data from your source, you might be using merges, or you might be deleting data due to GDPR or whatnot. Since Spark streaming does not know how to propagate deletes downstream, you'll face an error. And you can set ignore changes to actually process all the files that have been committed or changed as part of that transaction, and ignore the fact that some records may have been deleted. A gotcha here is that vacuum may delete the files referenced in the JSON files. So you would want to keep your tombstone or deleted file retention duration long enough, longer than however downtime you expect from your streaming workloads to make that faster. There's also the option to start your stream from a given version or timestamp, and that works by providing the option starting version or starting timestamp. And in that case, we'll just start tailing your JSON files at the corresponding version, and the same gotchas apply. Starting version and timestamp are inclusive, and the starting timestamp will start processing from the next version if a commit hasn't been made at the given timestamp, which is unlike time travel. So in time travel, you remember, if you provided, start processing at 1492, we would actually return the state at 1071. But with your stream, we're giving you the changes after 1492. Therefore, we'll actually start processing your changes inclusive of 1072 going forward. So to see all of this action, I'm going to pass it over to Denny to give you a demo.
Thanks, Barak. Diving right into the demo, let's showcase why asset transactions are so important when it comes to working with your data. For example, let's go ahead and stream data into our Parquet table. Okay, so again, there's a function before that basically was called generate and append data stream. We were basically generating new data, and we're doing this in the Parquet format as indicated here with the Parquet path. Okay, and if you open this up, you'll notice in the dashboard that there is an increased input and processing rate, and here's basically the average batch duration. Once we verify that, then we can run this command here, cell26, to see the number of rows going in there. So if we wait a few seconds, we can go ahead and see an increase in the number. Like before it's 220, now it's 320. Simple enough. How about if I want to have more than one client do an insertion into that table? Well, what you'll notice is that when I open this up, there is no input versus processing rate, and sure, there's a batch duration, but basically there's no new data in. See, here's the first stream, data still going in, as you can see here, but the second stream, no data is going in. All right, and so yes, the count is increasing steadily, but there's actually no increase, or you can't have a second or concurrent stream go ahead and insert data into that table. So let's go ahead and stop all streams and redo the exact same test, except this time we're going to go ahead and run this with Delta Lake. So again, we're going to kick this off. All right, same function. The only difference is that I'm saying table format is Delta and the table path is the Delta Lake path. I open this up and we'll see data slowly and steadily inserting in this. Perfect, bam, just like that. All right, so if I go ahead and take a look at the counts, same idea. There's going to be data showing up. But then what's really cool is that I can run a second stream and a third stream, and for that matter, I can even run a fourth stream if I want to, but I'm just going to run these two streams at the same time concurrently with the first stream. So now I have 3 concurrent streams inserting data into the same Delta Lake table. And you'll notice that here's stream number 2, and again, the input and processing rates are going up. And same thing for number 3. So there's data going in, okay? So all 3 streams, you'll notice the graphs, there's color here, and that should tell you basically that data is going in. So that's pretty cool. So now I've got 3 streams inserting data into my single Delta Lake table concurrently. All right, so let's stop the streams for now and just take a look and review what happened. So I'm gonna go look at the Parquet table, all right? And I'm just simply grouping by stream number. Basically, each stream that I insert, they have their own unique number. Okay, so I'm going to go ahead and do an insertion here. And so there's only stream number 1 for the Parquet and about 1,020 rows inside here. But if I go ahead and run this against my Delta Lake table, okay, delta.ml loan select state, you notice that there's actually 4 streams. The 0 stream, the reason 0 exists is because that was the initial insertion of the 50 rows of data that I placed in my original table. And then here are the 3 concurrent streams. But you'll notice that actually the Parquet table only has 1, while the Delta table has 4. Okay, this is happening because the insertion of the new data had a slightly different schema than the old data. Okay, and because it did, it basically ran over and corrupted the original Parquet table. In the case of Delta Lake, I've got all 3 streams inserting new data in, but I did not lose the original table as well. So that tells you how powerful it is, because even within the context of schema enforcement or schema evolution, you're able to ensure that you keep all the data and your data does not become corrupted in the process. So underneath the covers, back to what we originally shown in the demo, there's that Delta log folder, right? And what that described table history is actually looking at all the files inside here. Okay, so there are 25 JSON files corresponding to the 25 history. Okay, there we go. Versions, okay, of the table. So that transaction's all there. All right. So as Brock had described before, every 10th one, there's a checkpoint Parquet file created as well. All right. So that's where the V2 portion of this is not just the second version of this particular session, but we're actually referring to the V2 checkpoint. All right, well, let's just take a look at what the JSON looks like. All right, so we just open this up, and it'll break down the schema, information like what files were added, the commit information, and various operational metrics are all stored inside here, okay? And so if you want to take a look at it, for example, here's the commit information, just run this command, open this up, and the same operational metrics that we talked about, they're stored directly in that JSON file that you saw in the described history, okay? And the various operational parameters for that matter as well, right? The fact that we're doing an append. All right. In terms of add information, this will tell us what data was changed. This is for the very first one, so nothing changed yet, but we actually tell you which file is involved. Remember how Brock has also explained that the CRC file contains the table size in bytes and the number of files for dynamic partition pruning? Well, let's take a look at the CRC, and here it is. The table size bytes, the statistics that it needs, right? And as well the number of files, so it knows how to partition prune. In this case, this particular example, we're not actually using partitioning, so there's not much to prune here, but nevertheless, that's the context, okay? Now, let's take a look at the checkpoint file, right? And remember, V2 has some improvements. The main improvement actually is called out here. Under the add, when we're adding new files, i.e. adding new rows, we have stats, which is a string, which is what the way it was originally in the JSON file, but we also have stats parsed, okay? So the number of records, the minimum values, max values, null counts, things of that nature. So that way, the statistics are actually in columnar format, so it's easy for Delta Lake to actually grab this information and know how to actually set up the statistics better and actually run the query plans better. The key thing here is the add information. Here's the file that was added, path. Okay, here's the exact file inside the system. It tells you the size, its modification. Now, when you read the stats, you could try to read stats by itself, but again, that's just a string. Or, for optimization purposes, you can read stats parsed, which now you have the different columns for the number of records, the min values, for example, in this case, Iowa, right? Oh, sorry. And the max values, and the null counts, okay? So all that information is right there for you to be able to work with. Well, that's it for the quick demo on the V2 checkpoint. But again, this notebook will be available for you to download. So that way you can run this yourself. And so you can see this, how this works in when you combine it back with Brock's presentation.
Thank you everyone for listening, and we're happy to hear your questions. And as you can see, I've just rolled back to my shaven state again. So bye.